today, let me go through these with you. This is 722, and the reason this one was chosen is because it's important to understand that this is actually an algorithm that's used to create a cosine waveform. If you don't have an oscillator on a chip, you can get it this way. And let me just say this. First of all, they said that they want us, you're to prove a difference equation does this. This is 722. This proves that the output y of n will be cosine of omega naught n u of n. Now, what they want you to do is prove that this will be the case if this difference equation is executed properly. Problems like this I do give on the final. They're not proofs, but I'll explain in a second. So the difference equation that they have is y of n minus 2 times cosine of omega naught times y of n minus 1 plus y of n minus 2 equals 0. And they have some initial conditions. They say y of minus 1 is equal to cosine of omega naught, and y of minus 2 is equal to cosine of 2 omega naught. So these are the initial conditions. Now, really, all this stuff starts at n equals 0. The n equals minus 1 and minus 2 are the initial conditions. Do you understand that? That really, these are all for one-sided transforms. The minus 1, minus 2, just a little bit before 0, are ultimately the initial conditions. Mm-hmm. Are you with me, class? Yes, sir.
What's the point of the second equation? Is that like the given or?
No, this is something you got to prove. You prove that this is what's going to result from this equation right here. All right, that's the actual problem. Did anybody do this one? Or look at 722? If you did, you see that what they're saying is this algorithm is used on DSP chips, digital signal processing chips, right now. It's a real algorithm. So it's a good one to actually get a handle on. When you take a look at this, we're going to do the Z transform first of all this. All right, class? If you do the Z transform of both sides, that becomes just y of z. This will become minus 2 times cosine of omega naught, and then it's going to be times y of z, right? Divided by z, correct, class? Because it's z to the minus 1 in front of there. Do you all agree with that? Mm-hmm. But you also have to do one thing. You have to add y of minus 1 here, correct? Right? The initial condition appears. The next one is plus, well, the z transform of y of n minus 2 is y of z divided by z squared for starters. So then you get plus y of z, right, over z squared. Then it's plus what?
You want y minus 1 over z.
Plus y of minus 2, correct. Now, again, this whole thing is equal to 0, correct, class? Please just take a look at this. Y'all agree with me? I want you to make sure you understand what I've done. I've taken the Z transform, and because the initial conditions are not 0, there's a y of minus 1 and y of minus 2. The initial energies are there. You have to include these values. Now that cosine of omega naught is a constant. Omega naught could be pi over 2, it could be pi over 3, it could be pi over 9, it could be anything. Follow me? It's not nailed down. So these are just constants, but there is a relationship here. One other thing about this one. This is equal to 2 times cosine of omega naught minus 1. And that's an identity you can prove. You can get it from Euler's. Remember I always told you to go to Euler's if you're ever really stuck with something? But I'm just going to give it to you right now. Now, when I go from here, what I'm going to do is group all the y of z terms by themselves. So I have y of z. Before I do that, let me just do this for you. Walking around with a head, right? Now we know what we're really going to do is get y of z as a singular function on that side, right? And then when we get that, what we're going to do is see if indeed it fits this form, the z transform of this. What is the z transform of cosine omega naught n u of n? Well, some of you remember this one. Do you remember when I had a to the n cosine of omega naught n u of n? That actually transformed as what? Z squared minus what? Az times cosine of omega naught, right? Divided by z squared, right? Minus 2az cosine of omega naught plus what? A squared, right? Y'all remember that? That's one you gotta know. Now here, what is A in the one that I've got here? 1, right? Isn't it? It's 8, and 1 to the n is just 1, isn't it, class? It's so really I'm just gonna make everything over there and here, all the A's 1, and that way we can be on our way, hopefully. So I'll get rid of this, and get rid of that, and get rid of that, and this becomes 1, by the way, because A is 1. Does everybody agree with me? So that's the form we want to fit. Keep that in mind. You follow me? Once I fit that form, then I have proved it essentially, because doing this last step is really irrelevant. So now when I take a look at this, I group all the y of z, so I have y of z. I'll stop for a second and let you write it down. Just think about what I'm doing. I identified a transform of cosine omega naught n u of n. So I know the form I'm looking for in the answer. When I'm going to be grouping all this stuff together, I'd like to get it to look like that. And that way the proof would be done. Do you agree with me, everyone?
Yes.
I want to make sure you see what I'm up to. All right. Here, I factor out y of z, I get 1. Then I factor out minus 2, right, times cosine of omega naught here, divided by z, because that's this term right here. Do you agree with me, everyone? With me?
Yes.
What else? Then I have
Just got 1 over z squared.
plus 1 over z squared, right, times y of z. And that's really all the terms that have capital Y of z in them. Do you agree with me, everyone? We talked about this last time. Now, everything else I take to the other side of the equation. Just take a look. It's not hard to understand. When I take everything to the other side, what do I get? Well, I have minus 2 cosine of omega naught times y to the minus 1 to the other side, right? That becomes plus 2 times cosine of omega naught. And what is y of minus 1? Right, can I make this cosine squared right here? Class?
Yeah.
Y'all agree with me here? Right? If this y of minus 1 times cosine, well, y of minus 1 is cosine of omega naught. So it's just cosine of omega naught squared. Correct, class? All right, let's keep going on this. What else do we have? That's this. I have to take this to the other side, right? So that's going to be what? Minus cosine, right, of omega naught, right, over z. Correct, class? Are you with me on this, everybody? And what about this? Minus cosine of 2 omega naught over really just by itself, right? Isn't that right? All right, make sure. Yeah, that's right. Isn't class? Just take a look at this. Y'all agree with that?
Yes.
All right. Now, I've done all that. I can take this one and this one together. Now look, if I have 2 cosine, well, tell you what I'm going to, I'll leave it like that for, well, no, I'm going to group. I'm going to say this is equal to 2 cosine squared of omega naught minus cosine 2 omega naught right here. And then I'm going to have minus cosine of omega naught over z equal to y of z times 1 minus 2 cosine omega naught over z plus 1 over z squared. Now you can almost guess the next thing I'm going to do. Remember, I want to fit this form right here. I'm going to multiply both sides by z squared. The order, I know what you're going to say is divide, but it's easier to multiply first by z squared, I think. Both sides. You all agree with me here, class?
Yeah.
Just look, I want a z squared here and here. So when I do that, if I multiply by z squared, then I get this becomes z squared.
Dr. Valency, cosine of 2 omega is equal to 2 cosine of s squared omega minus 1.
I'm sorry.
Cosine of 2 omega.
Right. My bad. There's supposed to be a squared operator there. My bad.
Yes. then you can group those.
Well, yeah, you're right. I wanna, yes, just leave it there for a second and let me continue with the z squared thing. All right, you're absolutely right about that. My bad. So if I multiply by z squared, I get this. Then I get this. This is 2z squared. Oops, sorry. Let me do it this way. This is z squared here, and this is going to be z here. That's a 2 cosine. I just multiplied by z squared. Now, what he just said is what and I'm sorry I made that mistake. I shouldn't be in such a hurry. Now, I want you to just follow me on this. Look at this right here. And look at this. If cosine 2 omega naught is going to be 2 cosine squared of omega naught minus 1, right? Substitute that in here. What do you get? It's going to be minus 2 cosine squared omega naught, cancels that one, and then it's minus a minus 1 would be plus 1, wouldn't it, class? Yes, sir? I couldn't hear you. What?
The
That's
2, it got lost.
Like where it says z squared minus, what happens to that 2?
There is a 2. It got lost because I'm in a hurry and I shouldn't be. Thank you. So far I made 2 mistakes. Keep a count. Let's see how many more in there. Are you with me, class?
Mm-hmm.
All right, now what I'm really getting at is this. This, when I do that substitution, will get rid of this one and leave only 1 there. You follow me, everyone? All right, so I'm going to just replace that and put a 1, because then I can get it all in here. So I have z squared here is equal to that, and then I divide both sides by z squared minus 2z cosine omega naught plus 1, and I get z squared minus z cosine of omega naught divided by z squared minus 2z cosine omega naught plus 1, and that is my y of z. And you'll notice that that's exactly what we should get here, which goes to the cosine, which means my output y of n will indeed be that. Do you follow me, everyone, class? So it proves what they claimed, that difference equation, in fact, is going to cause the output y of n to be a cosine oscillator, cosine of omega naught, for any omega naught you want, as long as the initial values are these. And this is important, and it's also impressive if you think about this.
Yeah.
Because now you have a built-in oscillator based on a difference equation, which is important to know for times later on. All right, that's the first problem. Second one, I think it's 26. Bless you. All right, next is 726. Now, I don't think the answers are right in the book for this one, but I'm going to do it. They have h of z equals z over z minus 1, z minus 2, right? And so I think we did this one in class before. I want to do it again, make sure everybody's on the same page. Now, if you have a book, if you turn there with me, first thing he says is he's looking for where the zeros are, and he's looking for where the poles are, right? And he also wants to know, is it stable? So is it stable, yes or no? How do you get the zeros? Just by taking one look at values. What values of z make the function 0? You always go to the numerator. It's only 1 and it is 0, right. Zeros are at z equals 0. Where are the poles? And there are 2 of them.
Z equals 1, 2.
Right, 1, 2. We did this one. Now, next question, is it stable? Without ever doing an inverse transform or anything like that. Yes or no?
No.
Why? You're right. One of the poles is what? Outside the one circle, right? It's at z equal 2, which is greater than 1, means it's unstable. So no, just by looking. Third thing they want is, I don't even want to look at my notes. They're asking for,
Difference equation.
oh yeah, difference equation. That's another one that you've got to know for Friday and other days. So I know that this itself is really equal to y of z, right? Divided by x of z. Please make sure you understand that. That's the definition of h of z, is it not, class? Now, that is equal to z over, then do the operation, z squared minus 3z plus 2. I just went ahead and multiplied it. Then multiply by x on this side, and then y of z here is multiplied by z squared minus 3z plus 2 here. And now to go to the difference equation, it's straightforward. Listen to me, it's not hard at all. If you don't know. I divide everything by the highest power of z. So now I get y of z, and it's going to be simply 1 minus 3z to the minus 1 plus 2z to the minus 2 equal to x of z times z to the minus 1. Most of you know that. Follow me on this? Now it becomes even easier. I know the only way I can get y of z from something is if I have a y of n. Right? The next one is y of z times minus 3z to the minus 1. The minus 3 is an automatic. It's a scale factor. If I have z to the minus 1 y of z, the only thing that can create that is y of n minus 1. You with me, everyone? The next one, I have a 2 as a scale factor. And I have z to the minus 2y of z. The power, the exponential power, is just the number of delays that occur. And this was going to be simply y of n minus 2 is equal to, what about over here? What is it? X of n minus 1. That's it. And that is it. That's the difference equation that would give you that h of z. And that's the way you do it. We did it before. Just want to make sure everybody's clear about this. Now the next part of this problem.
It's the response to the input x equals 2, negative 6, and 4.
All right, now they give you this. Please pay attention to this. This one, these are the ones on like quizzes and stuff. People mess up routinely. Unless they have thought about it seriously. They like to have analytic functions or something that they could take the z transform of based on property, based on things they know. For this one, I have x of n equal to, what is it again?
2, negative 6, and 4.
Minus 6 and 4. Is this the 0?
Yes.
All right, so again, the underbar means that's the point where it's 0, right? Now, to take the z transform of this, always think of the definition of the z transform. It's a summation, n equals 0 to infinity, right, of x of n times z to the minus n. First one is 2, right? Z to the 0, it's just 2. So now when I take x of z of this, I get 2, that goes right here. Then, actually, it's going to be minus 6. Minus 6, right, when I put minus 6 in here, it's z to the minus 1, right? Or divided by z. So I think about this, minus 6 over z. And then it's plus 4 over z squared. We've done this before. I just want to make sure you see this again, right? Next is get everything, really I want everything over a common denominator, z squared. So now I have 2z squared minus 6z plus 4 over z squared. And that can be given as 2 times z squared minus 3 z plus 2 over z squared. And that's my x of z. Right? Please just make sure you see this. There's nothing tricky right now. We did this one before. Then I go ahead and I say my y of z here would be equal to x of z times h of z. Just multiply the transfer function times h of z. Correct, class? Now when I do that, what happens? Here's my x of z. I have 2 over z squared minus 3z plus 2 divided by z squared. And then it's multiplied by h of z, which is that, which is z over z squared minus 3z plus 2. Do you agree with me, everyone? I'm not trying to bore you, just making sure everybody understands this without me going on any further. Now, does everybody see the obvious cancellations? This cancels that perfectly, right? I have z and 1 over z gives me simply z down here, right? So this is equal to 2 over z. Now here's where people get stung. That's y of z is 2 over z. Therefore, what is y of n? And this is what I like to make people think about. All right, if I have delta of n, what is the z transform of that, people? 1, right? If I have a delta of n, it is, does everybody agree with that? If I have a delta of n minus 1, it is?
What, a over z?
A over z, thank you. I want to make sure you see the logic here. Therefore, when I look at 2 over z, the scale factor 2 is like a. When I have it over z, it means it's really got a delay of 1, or this means my y of n here will simply be 2 times delta of n minus 1. Does everybody follow me on this? Now make sure you see this. I'm showing you that because here's what happens on quizzes. They see this and they're paralyzed. I don't remember the function. They're thinking of a to the n u of n. They're thinking of something like that. And it's extremely easy. What's a constant go to? What goes to a constant? It's a delta function, right? And every time you have a delay by one value, it's divided by z to that value. Keep that in mind. Does everybody get me on this one? Mm-hmm. All right, next. There's another part to this one, isn't there?
1, -1.
All right, then they give us this one. Give me this again. X of n is what?
1, -1.
1, -1. Is the 0 here?
Yeah.
All right. Just work with me on this one. We're going to do it together because this is a good one. Now, when I take a look at this, what's the z transform of this? X of z, class. Think about just turn the crank over there in the definition. N equals 0, the value is 1. N equals -1, the value is, n equals 1, the value is -1, right? So you would have 1 minus 1 over z, correct, class? Another way of writing it, probably a better way, is z minus 1 over z. Agree?
Yeah.
Now, when I take a look at y of, I'm going to erase this part right here. Now when I go ahead and I take a look at y of z equal to x of z times h of z, again, by definition, that has to be the y of z. I go ahead and I put my x of z in as that, z minus 1 over z times h of z. This time I'm not going to use that form, I'll use this form, times z over z minus 1 times z minus 2. Again, I'm just going ahead and I'm substituting in the definitions of h of z and of x of z. Now, can everybody see the cancellation?
Mm-hmm.
Sure. I see that one of those poles is canceled, and I see the z is canceled, so I'm left with 1 over z minus 2. Now, this one, again, causes problems. But again, think back to what the delay operator does. So I know if I have 2 to the n u of n, that goes to z over z minus 2, right? Correct, class? But if I delay that by 1, if it's 2 to the n minus 1, u of n minus 1, in other words, I'm delaying this by 1, then it goes over here and takes that transform and divides it by z, or I get simply 1 over z minus 2. Does everybody follow me on this? All right, therefore, the y of z here for this one, or y then, pardon me, will be equal to simply 2 to the n minus 1 u of n minus 1. And you're going to see people do other things. What they'll do is they'll take 2 to the minus 1 out in front, or really 1 over 2. And then I'll have 2 to the n divided by 2. That's absolutely right. This can be written a couple different ways, but don't worry about it. That's essentially the right answer. Understand, class? Is there another part to that problem or not?
It wants the impulse response.
All right. Then they want the impulse response to it, and I'll do that right here. So when they ask for the impulse response, what are they asking for?
H of n.
That's right. They're looking for the inverse of that. So if I have z over z minus 1 times z minus 2, right? I told you divide by z first, didn't I? Remember that? Y'all remember when you do this? Usually it's the best way. Sometimes you don't have to do it this way, but if this is my h of z, I'm going to take h of z by z. So I have this, right? Then what is that going to be? It's going to be some a over z minus 1 plus b over z minus 2. Correct, class? You can almost guess these values. Do you agree with me? How do I get a? Cover that up and let z be 1. When it's 1, it is minus 1, right? Want to guess what b is? Probably positive. Cover this up, right? Let z be equal to 2. It's 1, isn't it, class?
Yep.
So this is 1. Right? Now multiply by z. Y'all understand? I just did division by z so I can get this. Understand, everyone, class? Now I multiply by z. This way you won't have that delay operator in there all the time. And I multiply by z. All right, now what is my h of n once we've done that?
Minus un.
Well, yeah, you're right. The first one is just u of n, but there's a minus sign. Minus u of n plus, go ahead.
2 to n, un.
2 to the n, u of n. And that's all it is. And there may be other forms of that answer, but that's essentially the right answer. Follow me, class? All right. Wanted to do that one. 26. I don't think, is there another part or not? Class?
No, sir. Okay.
Now for 28.
Okay, so impulse response is the same as h of n?
The definition of h of n is the impulse response of the system. It says if you put a delta function in, you get h of n out. And if you would put delta of t in, you get h of t out. It's always the system's response to an impulse as the excitation. That's it. That's the definition. Now, 28. Oh, we did 28 before, but I want to do it again. Y of n minus or plus n minus 2 equals x of n minus x of n minus 2. This is one of those, it makes you see patterns that are likely to crop up again and again. And the first part of this, I think they want the transfer function, right? 28. So if we take this, we're going to go ahead and take the z transform of everything. So we get y of z here, right? And then I get the quantity 1 minus z to the minus 2 power. And on the other side is just x of z times 1 minus z to the minus 2 power here as well. Right? And then to get the transfer function h of n, or h of z, pardon me, which is equal to y of z over x of z. Now, that's equal to, hold it, this is plus 1 minus z to the minus 2 over 1 plus z to the minus 2. I want to fit a form here. I know for transfer function I have to let z be equal to e to the j omega. That means this is for for the frequency response. Then you're going to have to let z be equal to e to the j omega, because the coefficient rho is set equal to 1 for this particular thing. When we do that, we see that probably the best way to do it for h of e to the j omega equals z would be to multiply top and bottom by z. So I have z to the minus, or z to the plus, I'll just put it as z right here, minus z to the minus 1 over z plus z to the minus 1, and then replace the z by e to the j omega. Now, I think you know why, and I'll do it up here. So now I have my h of z equals e to the j omega here becoming e to the minus j omega minus e to the plus j omega minus e to the minus j omega over e to the plus j omega plus e to the minus j omega. And this is something you have to recognize all the time. When you see those kind of exponentials, either subtractions or additions with if they're conjugate arguments of each other, you know you're thinking sine or cosine. Now the top one right here would be equal to j2 times the sine of omega, and the bottom one would be 2 times cosine of omega. This was something we've done before. Do y'all remember that? How many remember doing this? Now that is got to be what? The 2's cancel, but sine over cosine is just j tangent of omega, isn't it, class? And that's it. That's the transfer function for that's really, would be called, the frequency response would be given by that, and you could sketch it if asked. It's just a tangent function. That's all it is. The j means the phase is 90 degrees. Now the second part of that is what? Is there a second part? Well, I'm going to give you a second. Here's a question that could come up. Now, I'll say that this is the difference equation, and I want the output if x of n was equal to, say, 2 times cosine of pi over 4n u of n. So now I want the output for that. If that's x of n, I want to know what the output is. All right? Now write this down. I put it up on the OneNote thing, but I don't know how many people focused on that. If you have any system where you have an x of n going in at a constant frequency, so I'm just going to say x of n should have the form some a cosine of omega naught n plus some phase angle phi. This is what my x of n is going to be, fed in. It's at a constant frequency. The phase angle allows it to be a sine, a cosine, or anything in between, any combination. It's fed into a system with a transfer function, h of e to the j omega, or just h of omega for short. All right? And you want the output y of n. It will always be this way. I gave you a little proof on OneNote. I showed you this thing, how it was. Now, what happens is my y of n will always be equal to A, whatever that coefficient is, times the magnitude of H here, where omega is equal to omega naught. So now your omega naught is the coefficient of n. Follow me, class? What? You're shaking your head. Do you follow me?
I got a little lost after that.
It's just the magnitude of the transfer function. See there? Here's our transfer function. J tan of omega, right? If omega is pi over 4, what is the tangent of 45 degrees? 1. The magnitude of 1 is? It's J1, actually, but it's 1, right? So if you want. Then it's times cosine here. Cosine of omega naught n plus the initial phase angle plus the phase angle of the transfer function. Now that's always the way the output will be for a system if the input has a constant frequency. And I try to show you that on OneNote, where I broke the cosine down into 2 exponentials, and I proved if you have an exponential frequency exciting something, the output is just going to be given as the magnitude of the transfer function with a phase angle that's due to the really the transfer function here plus the original cosine or the original exponential. Put it that way. So now take it over here. I give this as the input, right? My output now y of n for that system, that difference equation which renders this transfer function, this frequency response. Please focus now. Will be equal to the magnitude of the input right here was 2, right? What is the magnitude of the transfer function when omega is equal to pi over 4? Because that's my omega naught. Take a look. Tangent of pi over 4 is 1. So it's 1 times 1. Then it's times the cosine, right, of pi over 4n, right? That was the original one. There was no original phase angle in here, right? If there was, I'd have to put it down. But I have a second phase angle. What is the phase angle of this one? When this is 1, what's the phase angle always there? What is J? It's pi over 2 radians, exactly. Don't put degrees in here. The book did that. It's wrong. It's got to be in radians, pi over 2. Now listen, why I'm saying that is important. You see how this is a radian value here? That means this has to be radians. You can't mix radians and degrees. So make sure everything's in radians in that argument. Understand, everybody? That's a common mistake. In the book, he makes that mistake, and it wasn't caught before it went to the first publishing site.
Okay.
Got me on that? If you look at OneNote, it shows you the actual proof. All right. Next problem. That's 28. I think it was 29. I got one thing to show you. By the way, before everybody blows out of here, how many are going to the game? 1, 2, 3. Very well, good luck. I hope you win. I hope you have to stay through Monday. 29. They give x of n. This is 729 equal to cosine of pi over 2n, and they give you a difference equation y of n equals x of n plus 0.5 x of n minus 1 plus x of n minus 2. And the first thing I want is h of z, I believe. You correct me if I'm wrong. Now the answers are skewed, all right? When you look at the answer for 30, it's not there. So if we want the transfer function h of z, which is what? Definition is y of z over x of z, correct? First thing we got to do is take the z transform on both sides. This is a gimme. It's an easy one. So when I take a look at this, I get y of z, right, equal to x of z, and follow me. That's just x of z, so there's a 1. This one, does he have initial conditions in there, by the way, for this problem? 729? Can you look? None? No initial? All right. Then this one is just going to be plus 0.5 over z, right, times x of z, and I factor out the x of z, plus, and then it's going to be 1 over z squared here times x of z, right? Does everybody follow me on this? Now when I get the transfer function, h of z equal to y of z over x of z. Lo and behold, I have 1 plus 0.5 over z plus 1 over z squared. And that's absolutely the right transfer function. It's that simple. But he wants the frequency response, doesn't he, in the problem?
Yes.
All right, so now we let z simply become e to the j omega. That's it. So now I can say my h of z becomes e to the j omega is simply 1 plus 1/2 times e to the j minus j omega plus e to the minus j2 omega. Y'all see how that can happen? That's it. That's the response. Now what does he ask?
Compute the output y of it.
Say again?
Compute the output y of it.
For that x event, right?
I assume.
Does everybody follow me in this? Now watch. First, what is omega naught? Just look here. Omega naught is pi over 2. Correct, everyone? So now we find out what h is when it's e to the j pi over 2, or omega naught is pi over 2. That's 1 plus 1/2. What is e to the minus j pi over 2? Minus j, that's right. So it's really 1/2 minus j over 2. And what is e to the minus j pi?
-1.
Does everybody agree with that, class?
Yeah.
It's -1. Or it's simply just minus j over 2, or that is simply 1/2 at an angle of minus 90 degrees, or minus pi over 2. That's the phase angle. I'll call it minus pi over 2. All right, now what would the output be? If that's the input x of n, your output y of n always is magnitude of that coefficient, which is 1, you follow me? Times magnitude of the transfer function. Well, what's the magnitude of the transfer function? Pardon me?
1/2.
1/2, that's right. So it's going to be equal to 1/2. Then it's going to be the same cosine operation times pi over 2n plus, and what's the phase angle? Minus pi over 2, or minus pi over 2. And that is the output. Now, the strange thing is, that is also the definition of a sine. So it could be rendered as 1/2 times the sine of pi over 2n as well. And that either one's correct. The book has that as the answer, by the way. What's the next part?
That was it.
That's it. And
You're at time too, so.
I'm never out of time. I'll never think I'm out of time.
Doesn't the university send the classes in 150?
Oh, that's the university, that's not me. I just wanted to tell you what I didn't get to. The DTFS is the thing I'm going to cover. This is the, you remember when we had continuous time Fourier transfer, Fourier series operation? When you had a continuous function, and we had an infinite series, Fourier series? Well, here we're going to have a discrete periodic waveform that goes on forever. We're going to get a discrete Fourier series, and that's on Friday.
These will be.
Yeah. I mean, again, good luck at the game.